Hello everyone, here is the video for exam theory review in Organic 2. The first question is naming. We would like to name these four compounds. Compound A, it is a carboxylic acid. So I should put number 1 on the carbon connecting to the carboxylic acid. Then 2, 3, and 4. So on carbon 4 we have bromo. So 4 bromo. Then the name of ring is cyclohexane. Then carboxylic acid. Compound 2, it is an anhydride. And if we take a look to the structure, we can see on each side of anhydride we have only one carbon. So the acid associated with this piece is formic acid. And both sides is identical. So the name of this anhydride is formic anhydride. The third compound, it is an ester, and we should number it from carbonyl group 2, 3, 4. And we always first mentioning the name of alkyl group attached to the oxygen. So the name of this ester starts with methyl. Then we name the rest of the molecule. On carbon 3 we have chloro, so 3-chloro. Then our parent chain has 4 carbon. Instead of saying butanoic acid, we say butanoate. And compound D, it is a nitrile. So here is how we name it. Carbon 1 is belongs to the nitrile, 2, 3, 4, and 5. On carbon 4, we have fluorine, so 4 fluoro. Then parent chain has 5 carbon, so pentane, nitrile. Then for question 2, we need to complete these reactions. For step 1 or reaction 1, we have alkene reaction with HBr, but it is under peroxide condition. When we have HBr and peroxide, addition is anti-Markovnikov. So instead of having bromine on more substituted carbon, we will have it on primary carbon. Then comparing this product to the next step, instead of bromine we have MgBr. So it is synthesis of Grignard reagent. So what we need here is Mg, or we can write Mg and ether, because the solvent normally is ether or THF. In the next step, Grignard reacts with carbon dioxide, followed by acidifying the mixture. So instead of MgBr, we need to put a carboxylic acid group, because Grignard attacks to the carbon dioxide. So instead of Mg, we have CO, O negative. Then when we add acid on the second step, this O negatives converts to an OH. So we have pentanoic acid. In next question, here we have cyanide. So it is SN2 reaction. Cyanide can attack and kick bromine out of a structure. Here we have a cyclohexane with cyanide group. Then on next step, we are going to have addition of Grignard to the nitrile. We know when we have addition of Grignard to nitrile, if I show the nitrile in triple bond, then CH3 negative attacks to this carbon, push electron to the nitrogen. So we expect to have a C double bond N and a CH3, and this N should be negative. When we add acid, instead of having NH, we will have oxygen because the imine under acidic condition is not stable and it can convert to carbonyl group. Next reaction, here we have 2-bromobutane and we synthesize this compound by addition of HBr. This carbon is primary, this carbon is secondary, this carbon is secondary, and this carbon is primary. We can write this alkene, then bromine adds to the secondary carbon. We can also draw this alkene, and both of these secondary carbon, they are identical. One of them gets hydrogen, another one gets bromine. So both of these two structures are correct. The next step, again, we have SN2 reaction. Cyanide can kick this bromine out. Then we are going to have this compound. Then when we have cyanide by lithium aluminum hydride, Cn group converts to CH2NH2. Then I can have CH2NH2. Or it's better to draw the structure in this form and put CH2NH2 here and put the methyl group here, this methyl group. Question 3, we would like to rank these hydrogen based on their acidity. Hydrogen A attached to the oxygen in carboxylic acid, so it's most acidic one. HB is on alpha position of ketone, C is on alpha position of an ester, and D, it is on alpha position of 2-carbonyl group. So 2-carbonyl group has more effect on acidity, and HD is the next. Between ester and ketone, always aldehyde and ketone, they have more acidity comparing to the ester. So then we have HB and HC. Question 4, we would like to draw the enol form for this carbonyl compound. So we need to mark the alpha carbon, then alpha carbon and the carbon for carbonyl group, they should be double bond. And C double bond O should convert to single bond. So if this is the alpha carbon, I put double bond here, and double bond O converts to single bond OH. Same for the next one, if this is the alpha carbon, I should put double bond here, then the OH here. And of course we have a hydrogen here as well. And we need to have one more methyl group here. And for the last one, this is our alpha carbon. It doesn't matter if we put it on the right side or left side when we draw the enol. Here are the answers for question 4. In question 5, again, we would like to complete these reactions. In first one, we have a reaction of alcohol, a primary alcohol with potassium permanganate. primary alcohol, they oxidize to the carboxylic acid. So the CH2OH converts to carboxylic acid functional group. Comparing this step and the next step, instead of OH, we have Cl. The only method we can convert OH to Cl is using thionyl chloride, SoCl2. And then the next step, we add an alcohol. This alcohol, I draw the structure here. It can attack, kick chlorine out. We know it's gonna open and close the carbonyl group. We just simply write it in this way to make it easier. And then pyridine can take hydrogen of alcohol. Eventually, we have an ester. So here is the structure for our product. If I rewrite the whole structure for acyl chloride, and instead of chlorine, I put oxygen and the rest of alcohol structure. Here again, we have carboxylic acid and thionyl chloride. So all we should do is converting OH to Cl. Then we can see that instead of Cl, on the next step we have NH2. So it's an aminolysis reaction, and we need to have ammonia as a reagent for the next step. Primary amide, when we have an NH2, they can lose one water, H2 and O here, and convert to the nitrile group when we use SoCl2. So instead of amide group, we should have a cyanide group in our last step. Here is another reaction for amide. First, we have an ester. We have aminolysis reaction, so NH2 can attack and kick the methoxy out, and then is losing one proton as well. So the structure for this step is an amide. Instead of O-methyl, we have NH-methyl. Then the next step is reduction of amide. When we have reduction of amide, we just simply erasing the carbonyl group, double bond O, and that carbon converts to CH2. So if I want to draw the structure for this step, I would write everything. I just don't write double bond O anymore. This is the answer for this reduction. In next reaction, we use sodium methoxide. So methoxide acting as a base, we have a beta keto ester. This is our ketone and this is our ester. So the hydrogen between these two carbonyl is acidic, and methoxide taking this hydrogen, converting this carbon to a negative carbon and enolate ion. Then this negative charge, this carbon can attack easily and kick bromine out in an SN2 reaction. As a result, here on alpha position, we will have an alkyl group from this reaction. Then the next step is hydrolysis reaction, acidic condition and heat. In beta keto ester, the ester functional group converts to the carboxylic acid. Then carboxylic acid converts to the carbon dioxide, a decarboxylation reaction, and leave the structure. So what is remaining at the end is this ketone. The next reaction, here we have an alpha bromoaldehyde, and here we have bromine in acidic condition, so our reactant should be the aldehyde. We just remove the bromine from this structure. Then the next step, we have pyridine. We use a base. When we use pyridine for alpha bromoaldehyde or ketone, we can have an E2 reaction. So pyridine take this hydrogen on beta carbon. Then we have HBr elimination. Then we are going to have alpha beta unsaturated aldehyde. We know alpha beta unsaturated aldehyde, they would like to react with most of the nucleophile from the beta position. And the next step is reaction of Gilman reagent, organocopper compound with this. In this reagent, the phenyl or benzene ring, it is a negative. It can attack to the beta position. So if you have a phenyl here, this phenyl negative can attack here and push the pi bond to the alpha carbon. Then the negative charge on alpha, it can neutralize by absorbing proton from the solvent. As a result, we have an aldehyde, and on beta position, we have a phenyl group or a benzene ring. The next reaction is reaction of carboxylic acid with PBr3, Br2, and then methanol. It is the Hell-Wohlhard-Zielinski reaction or HVZ reaction. The product always have a bromine on alpha position. If we add water at the second step, then we have the carboxylic acid with bromine. But because instead of water we use methanol, so instead of OH here we will have OCH3 regarding to the mechanism of reaction. The next reaction is reduction. We have a ketone and we have an ester group. Sodium borohydride cannot reduce the ester. So all it can happen is reduction of ketone. So ester group remain unchanged, but ketone converts to an alcohol. For question 6, we would like to propose a synthesis route for this reaction. Our starting material, our reactant, it is a beta keto ester. When we have acetoacetic ester, our final product is an acetone derivative. Take a look to this final product. We have the acetone molecule here, and on its alpha position, we have two alkyl group, phenyl CH2 or benzyl, and CH2CH3 or ethyl. So we need to add these two alkyl group to the acetoacetic ester. The first step is using base. So sodium ethoxide. We should use ethoxide because here we have O-ethyl. Then, for adding this alkyl group, we can add any of them for the first step and the second one for second step. So I would like to write here ethyl bromide. I could use phenyl CH2 bromide as well. So the structure for this part, we have the acetoacetic ester, and then we have an ethyl group on this carbon. Because this carbon with base get negative and attack and kick bromine out. Because this carbon lose proton, acid-base reaction, then the negative charge attacks to the ethyl group SN2 reaction. Now we can repeat this process one more time. Again, sodium ethoxide. Then for second step, this time I'm going to use benzyl bromide, phenyl CH2Br. Then here for product we have O-ethyl, we have ethyl here, and we also have benzyl here. Then when we have hydrolysis, the ester group converts to the carboxylic, leave the structure as a CO2. So in our product, we don't see this ester. What we see is the remaining. On alpha position of an acetone, we have ethyl and benzyl group. And here for the last question, it is a mechanism. We would like to show the mechanism for these steps. Comparing the reactant and the intermediate for first step, we see the OH attached to this carbon. So OH should attack to this carbon. And we also see that C double bond O converts to C single bond O. So when we have this addition, of course, carbon cannot have 5 bonds, so the pi bond should move to the oxygen and oxygen get negative charge. Then when we compare this product with the intermediate, we can see that again we have carbonyl group. So this negative oxygen should go back and make the double bond. And we see the OCH3 negative, it is out of our structure, is not attached to our molecule anymore. So that means by formation of double bond, OCH3 leave the structure. Then for the last step, we can see that OH converts to O negative and O negative converts to OH. So it's an acid-base reaction. O take hydrogen and then the electron of OH moves to the oxygen of carboxylic acid to make it negative. Thank you for watching this video. For watching more video, please subscribe to our YouTube channel.